Conservation of momentum in section 9. This is a good one. I like this one. So we have two balls moving toward each other, colliding and bouncing straight back. So kind of a unique situation. A lot of times they'll glance off each other, but this is bouncing straight back. According to the impulse momentum theorem, the change in impulse is equal to the impulse for both balls. So look at the picture. Ball 1, ball 2 headed straight directly at each other. They'll hit. Wow, it drew a square. We don't want that. Let me get rid of that. Okay. Yeah, maybe I should have left it. No. Okay, now we're not drawing squares. So here we are. We're going to bounce right there. And the change in impulse is equal to the impulse for both balls. So if ball 1's momentum increases by a certain amount, then ball 2's momentum will decrease by the same amount. Why would that happen? Why would ball 1's momentum increase while ball 2's momentum decreases?
Because one's sucking up.
Because of the direction.
Well, why? Why would that happen?
The direction.
Because one's traveling at
Mass?
Mm-hmm.
Mass. Ball 1's mass is,
less than. Wouldn't it be? Or would it be greater?
well, definitely different, right?
Yeah.
But we'll talk about it. But mass definitely would cause momentum of ball 1 to change and ball 2's momentum to be also impacted.
So what about velocity?
What about velocity?
Wouldn't that also cause that?
If ball 1 was moving faster than ball 2 and they hit, then ball 1 would maybe have a different velocity and ball 2 would maybe have a different velocity as well. Okay, and we know that impulse is calculated by what two values?
Change in momentum over time.
Okay, so and momentum is
Mass
times
delta V, pretty much.
velocity, basically, right? And you guys just hit on both of those two things. So the forces during the collision are an action-reaction pair. So we have force 2 on force 1 and force 1 on force 2. And we know that momentum is calculated with mass and velocity. So those two, mass and velocity, are going to be heavily involved in this calculation. So during the collision, we have this situation, and then after the collision, they are now moving in opposite directions. So what this is implying is we're going to be able to calculate the final velocity of each. We're going to be able to calculate the force on each. We're going to be able to calculate the impulse on each based on the information that we're given. And also remember that in the during phase, the forces that are going on while the impact is happening are much, much greater than the outside forces that would be influencing this. So we can ignore those. That would be like drag or gravity, like we talked about before. Okay, so the final implication here is that the total momentum of the system is unchanged. And that is conservation of momentum. And that's what this section is about. So we're going to use this conservation of momentum idea to be able to solve problems. And it actually makes life way easier using this conservation of momentum idea than the force problems that we were working on way earlier in this class. So here we go. If there are no external forces acting on a system, then the total momentum of the system is not going to change. So no friction, no drag, stuff like that. So for example, if we launch a cue ball at the rack of balls on a pool table, when the cue ball strikes the other balls, that is an external force. But after that, there's no external force, and the total momentum of the system is going to be considered constant. So assuming no friction and perfectly elastic collisions and so on. So the total momentum of a system is subject to only internal forces, and everything is conserved. So momentum final is equal to momentum initial. And that's total momentum when we use the capital P. Okay? So if you have an external force acting on the system to begin with, then you're delivering a change in momentum, and that change will be delta total momentum equals F net times delta T.
How come it's got like a weird little dash in there?
Yeah, so remember when the PDF is being formed from the file,
Yeah.
for whatever reason, on this screen, it doesn't transfer. Like if you look at the original PDF file, the arrow is perfect. Everything is fine. But for whatever reason, when it is transferred onto this screen, it just doesn't like the arrows above the letters. So it's supposed to be a solid arrow. I don't know what's going on. I don't know why that happens.
A minus and a plus.
Yeah, it's
Yeah.
so confusing.
No, I don't know. So that is just a single arrow. Okay. Okay. So where did I leave off? Yeah. So we have this formula here. That's delta total momentum equals the F net times delta T. And F net is the net force because of the external forces that are going on. If F net is 0, so this is very important down at the bottom, hence it's bold. The F net is equal to 0. The total momentum, capital P, of the system does not change, and the interactions within the system do not change the system total momentum. So we can have collisions going on, and the total momentum is the same. Okay? That's critical.
Where's
It's not down.
So the sum of the final momentum in each object can be set equal to the sum of the initial momentum of each object in component form. And this is where it gets really good. So momentum of object 1x final plus momentum of object 2x final plus, and so on, right? If we have all these objects in the x direction, final equals, so here's your equal sign right here, just don't get confused. Momentum of object 1 x initial plus momentum of object 2 x initial, and so on. Okay, so what this is saying is all of the finals added together in the x direction equal all of the initials added together in the x direction. Okay, and that's basically conservation of momentum. Now, all of the y direction components final would equal all of the y direction components initial as well if you add them all together. Okay, yeah, it's pretty easy. Okay, now remember that momentum is calculated by what?
Mass times velocity.
Right. So we can remind ourselves momentum equals mass times velocity, basically, if I'm just oversimplifying things. So each of those P's that you see there is actually an MV. Okay. So we use that to our advantage, and we take this. Two ice skaters, and we give them names, stand facing each other on frictionless ice. So Sandra has a mass of 45 kilograms. David is 80 kilograms. They push off from each other. After the push, Sandra moves off at a speed of 2.2 meters per second. What is David's speed?
It's going to be double that of Sandra's, or half, one of the two.
What we're going to do is we're going to write down everything that we have. The mass of Sandra is 45 kilograms. And the mass of David is 80 kilograms. Now,
we know that their final velocity,
their initial velocity is 0 because they're just standing there, right? They're facing each other, and then they're going to push each other's hands so that they push apart, okay? So the initial velocity is 0. So velocity Sandra initial is 0 meters per second. And velocity of David initial is 0 meters per second. This is initial, is 0 meters per second. Now, they gave us Sandra moves off at a speed of 2.2 meters per second. So we have velocity of Sandra final is 2.2 meters per second. Okay, so here's where it doesn't really matter which way you define the motion. David is pushing off and he's going opposite in direction of Sandra. So what is his final velocity going to be in terms of sign?
Negative.
It's going to be negative. He's going in the opposite direction, right? So we know that much at least. So I don't really need to draw a picture. I know the answer is going to be negative here, okay? So final velocity momentum, or final momentum, is going to equal initial momentum, and it's all along basically the x direction. So I don't need to write the x part.
So
I can just use initial and final.
if the initial, how does that work?
So let me write the formula. it is momentum, right? Momentum final plus momentum final equals, right? So we have, but I'm not going to write momentum. I'm going to write mass times velocity. So mass times velocity. So it's mass time of Sandra final. Oops. I don't want to write final. I don't want to write velocity final. So let me erase that. Mass of Sandra times velocity of Sandra final plus mass of David times velocity of David final equals mass of Sandra, velocity of Sandra initial plus mass of David, velocity of David initial. That's the conservation of momentum formula. Okay, so we always start with that. Now, what do we know?
Everything.
We know their masses, we know their initial velocity.
What do we know about their initial velocity?
They're 0.
It's 0. So this is 0, this is 0. Okay, so that means the entire right-hand side of this formula is 0. So now what is it I'm looking for?
David's.
David's final velocity.
So
Right.
we can, yeah.
So I'm going to solve for David's final velocity here. I'm going to move this term to the other side. So I have, and then I'm going to divide by the mass of David. So I have velocity of David final. I moved the mass of Sandra term to the other side. Negative mass of Sandra, velocity of Sandra final, divide by mass of David. This is a D. Okay, I can plug in my numbers. I have negative mass of Sandra, which is 45 kilograms. Velocity of Sandra final, which is 2.2 meters per second. Divide by mass of David, 80 kilograms. We plug all that into our calculator and we have what?
Negative 1.2.
Negative 1.2 meters per second. So they do not push back with the same velocity. And why is that?
Because David's heavier.
Because David has more mass. Okay? That's why. They push back with the same force, they have an action-reaction pair. But because David has more mass, the conservation of momentum to the system requires that David does not have the same velocity. Okay?
So that's basically.
So now we can use the law of conservation momentum to relate values of velocity and momentum of objects after the interaction to their values before the interaction. Okay? So after relates to before based on velocity and the mass of the system that we're dealing with. So clearly define the system. This is your strategy. If it's possible, choose a system that is isolated so that F net equals 0, if it's possible, or within which the interactions are sufficiently short and intense so that you ignore external forces for the duration of the interaction, using our impulse approximation that we were talking about before. While the collision is going on, we could ignore gravity and friction and drag, stuff like that, right? Then momentum is conserved. We want that to be the case. If it's not possible to choose the isolated system, then try to divide the problem into parts so that at least you can conserve momentum for something, okay? Other segments of the motion can be analyzed using Newton's laws or conservation of energy. What you're going to see is that conservation of momentum and conservation of energy, once we get to chapter 10, so the next chapter, the conservation of momentum and conservation of energy, seriously simplify the work that you guys were doing earlier in this class. And you're going to love basically what we're doing now and in chapter 10 because it's way easier stuff. So then draw a before and after. We want that before and after because it really helps us understand like what is happening, what happened during, and then like the physics of what's going on so we can write our formula correctly. Define what do I know, what do I don't know, and then the symbols that you're going to be using, and then the mathematical representation based on the law of conservation momentum. We generally want to solve for the velocities almost always because the mass generally isn't changing. So then you're going to use these guys right here, okay? And that's basically what we just did in that last problem with the two ice skaters. Almost always it's going to be just two things that are going on for us anyway. So this dot, dot, dot stuff you won't need to worry about. If you have things that are glancing off, then you're going to be working in two directions. So you'll have the X formula and the Y formula. But if it's just one direction, then you'll just have the X direction basically, and then you won't even need to worry about writing down X. And then just check that your answer has the correct units and that the answer makes sense. If you have something that was heavy in the first place, it's probably not going to suddenly be going wickedly faster than the other thing, right? Okay. All right. So the best way to get an old-fashioned wooden sled going, you can picture what an old-fashioned wooden sled looks like, on the snow is to get a good running start and then jump on the sled. Have you guys all done that?
Yes.
Yeah,
Okay.
of course.
Bailey is running at 4 meters per second and launching her 26 kilogram body onto the 5.9 kilogram sled. How fast is the sled moving just after she lands on it?
I like how it says she launched herself, not she jumped.
Right. Got to draw that picture, right? So before, after. All right. So what do we give her to Bailey? Bailey is running along. She has the sled. Now she's running. Let's see. Stick figure Bailey. Hair is definitely flying. She's very happy.
Give her a little.
Give her speed lines.
Speed lines. Good call.
Give her a little beanie.
That picture looks like someone from Peppa Pig.
Boom.
She's got a toque on her head. You guys don't even know what a toque is. Here's her sled. It's an amazing sled.
Wow. I run with the sled.
It's a spaghetti sled. You run with the sled?
Yeah.
But this says the best way to get the old-fashioned wooden sled going on the snow is to get a good running start and then jump on the sled. So the sled is motionless. So yeah, I agree. You run with it, hold the sled, and that way you have a better shot at landing on it. But she has not figured that part out yet. She's not as advanced as we are.
She's gonna go too far, and then the sled's gonna run her over.
All right, velocity of the sled initial equals 0 meters per second. Mass of the sled equals 5.9 kilograms. Okay. What else do we need?
We know the velocity initial.
We know the mass of Bailey is 26 kilograms. And
The velocity of Bailey initial.
how fast is she going?
4.9 meters a second. So like 10 miles an hour.
Yeah, she's moving. She's serious about this one. Okay. Now what?
You have to picture her on the sled with lines.
Right. So she's on this amazing sled. Let's see. There we go.
Dang, she looks like a witch on a broom from that picture.
What? No, it's clearly a sled. All right. See? Now she's going really fast. All right. What do we know?
We don't know velocity finals or anything like that. We just
Yeah, velocity final.
So okay, since now it's a system, would we add the mass of her and the sled?
Okay. So good question. The mass of the sled and the mass of Bailey are now together, right? So what do?
Adam.
Adam?
Mass of the system.
Adam, who's Adam?
Adam. Mass. Do we call it just mass, or do we say ms plus mb, msb? What do we do?
SB, BS, MBS, please.
No. So there's a couple of schools of thought here. Maybe when we go to do this, we would say we would not do just m here, and in the formula we would write ms plus mb. Maybe here, since we know both of those, we would go ahead and add them together. Let's go ahead and do that. What is 26 plus 5.9?
31.
So we have 31.9 kilograms. Okay, and what about the velocity final?
That's what we're looking for.
That's what we're looking for. Okay.
So our equation would be ms times v s sub I, which
Mass
is
of the
0.
sled times
The velocity of the sled initial.
velocity of the sled initial.
B.
So plus mass of Bailey times velocity of Bailey
initial equals velocity final times mass.
Mass
Because we have
of the combined system times velocity final. Good.
So really all we gotta do is what? Divide by mass.
And what do we know here?
Velocity initial for the sled is 0.
So that guy's out of there. And so all we have left is these terms
Divide
on
by
both sides.
mass. Divide by mass.
Divide by mass of the system. That's right. So we have mass of Bailey times velocity of Bailey initial divided by the mass of the system equals the final velocity. The mass units divide out and you're left with velocity units equals velocity units. So we were good.
3.2.
The mass of Bailey is 26 kilograms. The velocity of Bailey was 4 meters per second. The mass of the system was 31.9 kilograms. And what'd you say we get?
3.3 meters a second, including significant. It's 3.20 something, but with significant figures. It's
So 3.3 meters per second?
Yeah.
Okay. Great. So she was moving at 4. She lands on the sled. How come she slowed down?
Because the mass of everything
Because the sled had to skip going.
Because the mass of the system
increased.
So conservation of momentum says we must slow down a little bit. That's why.
That's why you run with the sled. You go faster.
If you can get your speed up a little bit, if you can still run at 4 meters per second while holding that sled, then you don't slow down when you hit the sled.
Why not just turn yourself into a slingshot and like set up, 2 giant poles and
Like
blast
angry.
So explosions are not the explosions that you're thinking of, but explosions are when particles of a system move apart after a brief, intense interaction. That's what the definition for explosion would be for us in this class. Not as fun as it sounds, but they can be. So the explosions are just the opposite of a collision. Objects coming together are colliding. Now, if we were together and we explode apart, that's all it is.
like
So
a
the-
grenade.
Okay.
The ice skating, that was an explosion.
That wasn't very intense, but that's the idea.
So
Okay.
like a grenade.
A grenade. Okay, sure.
It's an explosion.
This could be from an expanding spring, though. That would be, if it was an intense expansion on the spring, that would be an explosion. An expanding hot gas, that would be an explosion. Okay. So these are internal forces. So if the system is isolated, the total momentum during the explosion would be conserved. So if you have a spring that's compressed and it's just sitting there, and then all of a sudden, boom, there it goes, and it expands out, that was an internal force that is being released, and that is conservation there as well. So we have a 30-gram ball being fired from a 1.2 kilogram spring-loaded toy rifle with a speed of 15 meters per second. What is the recoil speed of the rifle? So what is recoil speed? What does that mean?
An explosion.
No. What's recoil?
That's when the gun kicks back.
Right, that's the kickback. So the ball or the bullet or whatever it is that's being fired is going forward, but there is recoil backward.
So that's the momentum.
That's conservation of momentum. That's right. That's why there's
Darn it.
recoil. Okay. Now the recoil is nowhere near as fast as the thing that got fired out, but they are what was the word that we used for
So
we have a force going one way and a force going the other way.
explosion.
What are those called? Action reaction pairs. Okay.
No, for a bullet, though, that's not going very fast.
Well, so if you make the rifle heavier and heavier, does that mean that the
recoil is going to be less.
recoil would be less?
So the felt recoil would be less, yeah.
Or if you increase the delta T, like adding a butt pad,
Uh-huh.
that would also.
Yeah. And that's why some stocks would have that thick rubber pad on the backside of it to help with the recoil. Yeah, absolutely. Okay. So what do we do?
Oh my gosh.
What is the recoil speed of the rifle? What do we do?
Does this really
Draw a
get before
picture.
and after? I don't think it does because we can picture it.
We know what a gun looks
We
like.
need a before and after. Sure. We're going to follow the procedure because that's instilling that type of the practice that we need for problems that we don't understand very well. So before, after. What do we know?
You just got a gun sitting there.
I don't need to draw a picture. Let's just label everything the way we want. What do we know?
We know the mass,
Mass of what?
the rifle, it's 1.2 kilograms.
So the combined mass then would be what?
1.2.
Because everything's sitting in there, right? Internally.
Yeah, it'd be 1.5.
So 1.2 kilograms spring-loaded toy rifle plus 0.3?
No.
0.03.
It'd be point.
It's 0.03.
0 point, move the decimal, 1, 2, 3. It's 0.03 kilograms. So 1.23 kilograms. Okay, what else do we know?
Velocity initial equals 0.
Okay, meters per second, right?
Yeah.
Okay, now after.
You hail.
Now you have the mass of the ball.
The mass of the rifle and the mass of the ball. Let's say mass of the rifle first.
1.2.
1.2 kilograms. The velocity of the rifle,
That's what we're looking for.
final. Don't know. Okay, mass of the ball is 0.03 kilograms. Velocity of the ball, final.
15 meters per second.
They said 15 meters per second. Now, this type of problem, this setup is exactly the same if it wasn't a toy rifle and it was actually a real rifle and you were firing an actual bullet and you had the velocity of the bullet and you had the mass of the rifle. Same exact problem, just different numbers. Okay?
A lot bigger numbers.
Bigger numbers is all. Exactly. So, what do we do?
Set up our equation.
What is it?
So MR times VRF plus MB times VBF.
Mass of the rifle times the velocity of the rifle, final, plus mass of the ball times velocity of the ball, final, equals
Velocity initial times 1 point, or the
0.
mass. Of the
so what is it?
Mass times velocity initial.
Which is
0.
so it's
system.
0. All right, what is it we're looking for?
Mass of the rifle. So let's move.
Mass of the rifle.
No, the velocity of the
Velocity of the rifle. So
rifle. Move mass,
this guy is going to the other side.
then divide by mass.
So we have negative MB VB final, and we're going to divide by mass. So we have VR final. We're dividing by mass of the rifle. So we have negative mass of the ball, velocity of the ball final, divide by mass of the rifle. What do we get?
Negative 0.36.
Negative 0.36 meters per second. Negative makes sense because it's going the opposite direction of the ball. Totally makes sense. Meters per second here, the units are good. And is it small? Should it be small?
It says recoil speed of the rifle, not velocity, so it has to be positive.
Well, but does the negative answer make sense?
Yeah.
Because it's going in the opposite direction. Yeah? Okay, and this is a small number, and should it be?
Yes.
Yeah.
Yeah, because 15 meters per second up here with the small mass compared to a large mass should be a small
That should be
velocity.
barely felt.
Okay.
How much is
Yeah.
that in force?
Well, that small speed,
I wanna know
it's
what
not
the-
very fast,
The
right?
force
So
of it is. Yeah.
what's the force?
Yeah.
How do you calculate force?
Force of it.
Would be mass times acceleration.
Yeah.
So we take this 1.2 kilograms times some acceleration. How would we calculate the acceleration? Don't know.
We don't have a time.
Well, you're gonna, once you do 9.8 plus that acceleration.
9.8 plus, we don't have an acceleration here.
Yeah.
This is where chapter 10 comes in.
Okay.
Yeah.
Will we be able to find that out later?
Later.
Okay.
Now, rockets in space actually use the same idea as well. Conservation momentum principles are used for propulsion. So we have onboard fuel that burns. So if you picture like the space shuttle, I don't know, you guys, it doesn't matter. So we have rockets, right? And what they do is they burn this fuel and it spits out the exhaust, right? So for trajectory corrections and things like that, we spit out these exhaust gases, and in return, what happens is those gases push on the rocket. So very small pushes make very nice little adjustments for us, and we can correct all of our trajectories that we need to do in space. So because of the law of the conservation of momentum. So that's how we get around in space.
I wonder what would happen if you didn't have this on.
Well,
This one, we're almost done. An explosion in a rigid pipe shoots 3 balls out of its ends. So this is an explosion inside of a pipe. We have 3 balls shot out of the ends. A 6-gram ball comes out of the right end. A 4-gram ball comes out of the left end with twice the speed of the 6-gram ball. From which end, left or right, does the 3rd ball emerge? Think about it.
It's like a
I
real.
know what the answer is.
So they're all 3 balls are sitting here in the middle, right? And they all come out at kind of at the same time, right?
Obviously,
They're not going to sit there and bounce off each other. The idea is they all come out at the same time.
Oh.
So the first one here, it says the 6-gram ball comes out the right end. Okay. Now, because of conservation of momentum, the 6-gram ball comes out the right end. Fine. We got 6 grams over here, but it comes out with, let's say, 1 velocity. Okay.
Yeah, 1V.
So we say times 1v. So that's its momentum. Okay. But now we have the 4-gram ball coming out of the left end with twice the speed. Okay. So that means it comes out with 2v. So over here we have the 4-gram coming out with 2v. So its momentum was actually 8v. Okay. Or 8 momentums. Okay. Over here we have 6 momentums. Over here we have 8 momentums. That means we have to conserve momentum by applying 2 more momentums on the right hand side so that we have a balance. Does that make sense?
If these were all right, we just didn't know how we were right.
So we need two momentums on this side. The last ball, from which end, left or right, does the third ball emerge? It has to emerge from the right hand side. We don't know enough about the last ball, but we know that it has to come out the right hand side with some sort of mass and velocity to it. Okay, that's how you answer that question to maintain the conservation of momentum.
I thought my
Because